Um, Hi, Professor. This is the first time I'm doing a presentation in Zoom, so if my recording is not that good, I'm sorry about that. But I will try to share the slides. So if anything, you could follow up with that. The enzyme I have selected for the presentation is glycerol dehydrogenase. I don't know why I chose that, to be honest. I was just Googling, and when I see glycerol dehydrogenase, I feel like that has something to do with uh, fat catabolism, anabolism actually. So I just wanted to see how that enzyme works. So I do the research and I made the paper on that. So I'm gonna share my PowerPoint. Yeah, this is my PowerPoint. Glycerol dehydrogenase. Before I go straight to what glycerol dehydrogenase is, I really wanted to say a few things about enzymes. Enzymes are the reaction catalysts of biological systems. In fact, most of our biological systems wouldn't work really great if it is not for the enzymes. And most of the growth and development we see in all organisms is because of the enzymes. Because of that, enzymes are the most remarkable and probably one of the most specialized proteins. And as we know, enzymes are highly specific for their substrates. They accelerate chemical reactions and they function in aqueous solutions of under very mild conditions of temperature and pH. Enzymes usually function at certain pH levels, usually at a pH of 7. And the temperature they are really good to work at is usually the body temperature of 37 degrees Celsius. But there are certain groups of enzymes, especially the thermophilic enzymes, that are capable of working under extreme temperature and pH conditions. And as it can be seen on the picture, enzymes usually reduce the activation rate for the enzyme for the reaction, so that the reaction can go a little faster. Glycerol dehydrogenase. Glycerol dehydrogenase is one thing. It is a metal-dependent enzyme. It uses a metal cation. Usually, they could be monovalent or divalent. This enzyme is an oxidoreductase. That means it engages in both oxidation and reduction. I will go through which part of the substrate is being oxidized and which one is reduced in the later slides. And this enzyme, it oxidizes glycerol into glycerone, or sometimes, usually it's called dihydroxyacetone. And at the same time, it reduces NAD plus into NADH. And because of this, the enzyme is sometimes called NAD plus linked glycerol dehydrogenase. The reaction scheme for the oxidation of glycerol to dihydroxyacetone or glycerone is shown below, shown in the slide. There are alternative names that are given for this enzyme, sometimes called GDH, G1DH, glycerol DH, or glycerol NAD plus 2 oxidoreductase, because the carbon that will be oxidized is the second carbon of glycerol compound. Glycerol dehydrogenase enzymes that have been isolated from various bacteria. I have included all the lists of the researchers who have isolated these enzymes from these groups of bacteria. And the first one is Enterobacter aerogenus, and the second one is Klebsiella aerogenus, Streptococcus faecalis, Escherichia coli, Bacillus stereothermophilus. I don't know if I really said them the right way. But from these groups of bacteria. The last one, the Bacillus styrothermophilus, is the type of bacteria that has been investigated really well, and the glycerol dehydrogenase enzyme from this bacteria it is thermostable. It functions at various temperatures. For this reason, this is the enzyme that we see a lot of research related to it. Regarding the structure, this is not something I created. Actually, I found it online, and doing the PyMol for the enzyme is really difficult, even under your guidance. It was from various researchers, and this one looks one of the more representative PyMol image. And as most researchers show, this enzyme is a homooctamer. That means it consists of 8 identical monomer units, and each monomer, it has 9 beta sheets and at least 13 or 14 alpha helices. The enzyme is made of a single polypeptide chain, and that chain consists of 370 amino acids, and they all make up around 40 kilodalton. And as we know, one amino acid weighs 110 dalton. If we round it to 100 dalton, 370 amino acids, if we round them to 400, 400 times 100 is like 40,000 kilodalton. That's the molecular weight of the enzyme. Regarding its active site, the active site of the glycerol dehydrogenase enzyme is made up of the N-terminal and the C-terminal. When we say the N-terminal, it includes all the enzymes from enzyme 1 to enzyme 163. And from enzyme 163 from 1 to 162, it is the N-terminal. The C-terminal is from 163 to 370. So there is a deep cleft formed between these terminals, and that active site has 3 binding sites. These binding sites include the binding site for the metal, the binding site for the NAD+ nicotinamide ring, and the binding site for the substrate. For the metal cation, usually the metal cations we found in this enzyme are either the monovalent or divalent. Monovalent include potassium ion, ammonium ion, or sodium and lithium ions. For divalent cations, we usually find either zinc plus or iron. And the main function of these metal cations is to stabilize the alkoxide intermediate. We're going to see which alkoxide intermediate we are talking about in the next slide. And the second one for the nicotinamide ring, this one has a special Roseman fold. Roseman fold is shown in the picture here. It has alternating beta strands and alpha helices, and the binding site for this nicotinamide ring is usually known for its unique fold. And the last one is the binding site for the substrate. Usually the substrate binding site for the enzyme, for the glycerol dehydrogenase enzyme, it contains aspartic acid and histidine residues, and in addition, it has water molecules, and they all play a stabilizing role for the reaction mixture, or we can say for the transition state. This is the reaction mechanism, and as we can see, there is a nucleophile here. That nucleophile takes the hydrogen away, and doing so moves these hydrogens to the oxygen. And when oxygen is negatively charged, the two lone pairs will come back to the carbon, and they form a double bond. And doing so pushes the hydrogen to be a hydride ion and will be nucleophilic towards the nicotinamide ring. Therefore, the nitrogen that was positively charged now becomes with zero charge. It will have lone pairs, and because of that, the NAD plus is converted into NADH. So in the whole process, glycerol is being oxidized to glyceron or dihydroxyacetone, whereas NAD plus is converted into NADH. At last, this enzyme is ATP independent. That's why the bacteria used it to oxidize glycerol to glyceron. And it functions pretty well in anaerobic conditions, which helps the bacteria in the breakdown of glycerol. The enzyme engages in a base catalyzer mechanism like sodium hydroxide. And what's being oxidized is the second carbon of glycerol. Because of its role in the breakdown of glycerol, biodiesel production companies are showing interest towards this enzyme because glycerol refinery is getting expensive day by day, because glycerol is one of the byproducts of biodiesel production. So in the future, we might see a lot of research is conducted on this enzyme, and industries might start using this enzyme. That there are other researchers who doubt the implication of the industrial use of this enzyme, because there are a lot of side reactions that are going on with, like we know as we know with a lot of enzymes. So if we can avoid these side reactions, probably the enzyme could be used even for more research. This is all I have for glycerol dehydrogenase enzyme. I hope you enjoyed my presentation, and I hope this something is not that bad after all. Thank you so much for listening, Professor. Thank you. And these are the references I have used